You say that unless there's an astronomical distance like Jupiter or something, that we're basically all in the same time. Now, how do you explain then, if say I'm in San Francisco and it's 7 in the morning, and you're in Rome and it's, I don't know, 4 o'clock in the afternoon or whatever the time is there, then you seem like you're in the future to me, but yet I'm not your past because it hasn't happened. How do you explain this time difference, or is it just a man-made thing?
Good. So let me take this question seriously. You presented this a little bit joking, but it's look, for many centuries, people on Earth didn't have to think that we are in the same temporal situation, because there were no telephones, there were no telegraph. Traveling was traveling by horse at the fastest way. So every place had its own time, and there was not even need to accord clocks. And in fact, until the 19th century, time in Bristol was different than time in London, because midday, 12 o'clock, was when the sun is at the zenith. And the zenith is in London half an hour of 20 minutes before, I don't know, than in Bristol, right? Because the sun goes. So each place has its own time, and you would go on your horse, go somewhere else, and readjust your time quite without any problem. The very idea that we have to have the same time came only when telegraph and trains come in. And then people started debating, can we agree on a common way of time? And for a while there was this suggestion that everybody would use London time. Of course, the suggestion came from the British. And people were not very happy about the rest of the planet, and the Americans were and then said, well, let's everybody have its own time, this is going to be a mess. So then there was a compromise. So let's slice the planet in how you say, segments, time segments, and at least we have the same time but then we know exactly, we jump 1 hour, okay, so we are at most half an hour or something out of proper time. And then came, trains and the need to have very precise timing, and so there were a number of projects to synchronize the time between the train stations. And this was already the end of the 19th century, the beginning of the 20th century, and there were some patents which were presented for the best way to synchronize clocks. And in fact, one of the patent offices where these patents were debated, how to synchronize clock, was in Bern, Switzerland. And there was a young clerk there who was analyzing these patents, how to synchronize clock. His name was Albert. His last name was Einstein. And that's the work he was doing. He was evaluating patents to how to synchronize clock between the train station of Europe in order to knock them out of time one another. And the guy realized that to be precise, this is totally impossible. So in the moment in which Europe got together, Europe, I also mean Britain. Sorry. In the moment in which, so we all get together to say, let's put the clock seriously at the same time, in the same years, Einstein realized that that's impossible. So you see, there is a crossover thing. There's a geographical thing. There's a cultural thing. There is a historical thing. But the point is, the final point is that saying at the same time doesn't make any sense if we want to go precise.
We have a question over here. Yes.
Hi, that was a great talk. Thank you very much. You've been talking about a linear, universal, observable time, and those are three things. Then you're not talking about a multiversal, non-linear, and non-observable time. But let's talk about non-observable. If you don't see time passing, if you can't see things changing, does time pass?
Well, the linearity of time is the fact that time is a single one-dimensional line, and something I said is just not there. We know it's not there.
But if you can't see it, if you don't see it, then you don't know that it's passing.
Right. So the observability of time is exactly what motivated us in quantum gravity to get rid of the time variable altogether. Somehow, once you get confused about time, you make one step back and say, what do we mean by time? It means what I observe in my clock. And then you ask, is the clock represented my theory? And you say, yes, it is, because in the clock, in my theory, there is I can put the matter that describes the clock and how it changes. So quantum gravity, what you do is you only put observable time inside, and you forget anything which is time with a capital T, which is not the clock time.
So is it different to quantum physics, where things can be in more places than one at once? Can you have more times in one place? Sorry, more times at once?
The things go together. In standard quantum physics, the textbook quantum physics is written when you study at university the Schrödinger equation. There is a T variable, but this is because that quantum physics assumes Newtonian time and background time, essentially. And also quantum field theory is the same thing. You assume background space-time. But it is regard generativity. Once you bring generativity in, that's an approximation. This T of the Schrödinger equation should disappear. You want to replace it with a reading of your clock and with observable time.
We've got a lady up there.
Oh, it's on. Okay.
Where are you?
Hello, up right at the top.
On the balcony, up, all the way up there.
Sorry. I have this light.
I find what you say about how the emotional aspect of time is what time is for humans, and also about how that's sort of the source of a lot of the suffering that we as humans go through. So I'm wondering if you, as a quantum physicist, have a strategy for thinking about time to try and alleviate that emotional suffering.
As a quantum physicist, I don't have any. I'm not different than any other human being. As a human being, I'll just try to deal with it. And in my little personal experience, I think the best thing to do is to follow the advices of the Buddhists. Just accept it. Accept impermanence. Deeply and fully, and then you realize that life is wonderful nevertheless.
Someone else down here. How about this gentleman just on the aisle here? Oh, you're going to have to duck under time to get there. Don't break it.
I was curious that you didn't really focus on aging or decay in your discussion around time.
Cheerful bunch, you lot, aren't you?
And I would have thought that is, from a human perspective, the most obvious thing that you relate to, because your brain decays. You have fewer brain cells, or you look at radioactive decay, you see a clear change there. How does that fit into the four metrics that you described?
In a simple way at first sight, in a horrendously complicated way if you want to go deeper. In a simple way because at our scale, where we can disregard the speed of light, we can disregard quantum mechanics and so on and so forth, we are immersed in, the Earth is clearly in a strongly entropy gradient, because we get the light from the sun, which is low entropy, or this high energy photon, and then they go out to the sky as low energy photon, which is much higher entropy. So we are in this flux, and this flux, the biosphere is strongly time oriented. So we live in this time orientation. Entropy keep growing. We keep growing locally, so it's fed by the low entropy of the sun, and the biosphere is strongly time-oriented, and it's just a working of entropy growing. It's a continuous disordering. That's what biosphere is. I think it's a mistake to think about life as a resistance to entropy to grow. Life is a way for entropy to grow. We are burned, like we're a little fire that burns. So we are a strongly oriented phenomenon, and as an strongly oriented phenomenon, we do things like burning, and in particular aging, and so on and so forth. This is a particular physics of us, which of course then becomes strongly emotionally meaningful to us, aging and dying. That's a simple answer. So within physics, we make sense perfectly what we're going. The complex answer is that things are not so easy because biologists tell us that there's no reason whatsoever for living beings to die a priori. Bacteria, to some bacteria don't die, okay? The actual evolutionary origin of death is at some point, and there's a big discussion in biology about that. Death has a purpose because to put it super simply, it's better for the species if the individual die, just to cut very big pieces. So again, there is a evolutionary reason for that. We're just a piece of nature following the law of increasing entropy, and the way to reflect emotionally to us is because then we have our brain and so on and so forth. Am I answering, or I'm just adding confusion to confusion? I hope you're not asking me why you're aging.
Right up on the balcony up there to the left.
You said the Planck length was the smallest amount of time possible.
Yeah.
What would half a Planck length be then?
Perfect. That's the right question. If this is correct, I strongly believe it's correct, but it's not something fully established in which we take it seriously. We have many experiments of them. In fact, we have almost no experiment of them. But if this is correct, the idea that you can slice time in smaller and smaller pieces is just wrong, right? They're just units of time. One bit of time is unbreakable. So to say a certain amount of time is to say how many units, how many bits of it. So the answer to what is half of Planck time is there isn't. There's nothing in the world you could not find ever half of Planck time.
Yes, here.
It seems to me that everything that's ever happened is in the past, and that everything that is yet to happen is in the future. So almost by definition, there is no present. Would you agree with that?
You're saying the present is very short, right? It's horrendously short. Yes, it's a boundary between it's the boundary between the past and the future is very, very short. That's certainly true for the present in Newtonian physics, no doubt. And it's also true if you think of space-time as a big picture. You have a slice, and what's over it is the future, and what's below it is the past, and the present is so thin that there's nothing in. But that's not the way the world is designed, right? So in space-time, the past is whatever is inside our past light cone. So it's whatever can affect us, whatever come in our past. And the future is this other opposite thing, this cone upstairs. So in between the past and the future, there isn't just a single line. There's a huge amount of time. A nanosecond, 5 nanoseconds between you and me. So in your life, in the history of your life, is a huge amount of time which is your past, for me, the past for me now, a huge amount of time there's a future for me now, and a nanosecond which is neither past nor future. If you lived on Andromeda, you probably would be green with antennas or whatever. A million years of your life would be neither past nor future for me. So the present is not thin, it's horrendously thick. That's Einstein's special relativity.
In the middle here, I think. There we go. Right in the middle.
Hi. Because you mentioned black holes
Yes.
and gravitational forces. I was wondering, because in space, gravity is different and there's less friction, I think. If you think that not only time is different, but because now there are humans in space, if our perception of time is going to be different? while we're there?
What do you mean by the question exactly? Our perception is going to be different because we as humans are going to be in space.
Yes.
Are going to be in space. Yeah, I think that what we call time, it's a multi-layered thing which depends on, which to some extent, to a large extent, depend on our perception. So whether they're humans or not humans is different because it's like colors, right? We see a color space which is three-dimensional, red, blue, and yellow, whatever. This is only because we have three different kind of receptor in our eye. So the three-dimensional, the way the thing is colored, it's only there because we humans see that way. So things are not colored unless they're humans. Now, if you ask how our perception of time is going to change the way we do interstellar traveling, it seems to me completely obvious it's going to change. Because in the moment in which, my girlfriend is an astronaut, she goes far away, she comes back, and she comes back 10 years later for me, but she has grown just 1 year. She's still young, I'm older. So we're going to get used to this growing at different speed, okay? Or maybe she comes back far in the future, 100 years in my future. I say, oh my God, my girlfriend is 100 million in the future. I've lost her. No, maybe I can get there. I just go also. I enroll in an astronaut and I go very, very fast and come back in the future. Say, hey, my girlfriend, I love you. We are back together in the future. This is physics. It's not science fiction. I mean, it's just an issue of money to build the starships and do that. If you could go, you said black holes. Black holes are slowers of time, very powerful, right? In fact, to some extent, the surface of a black hole, the horizon, is a place where the more close you go with a clock, the more it slows down. If you're very, very, very near to a black hole, you stay there for a while, you come out, millions of years passed outside. So black holes are stoppers of time, so to say, or just things that the black hole is something that goes from here very fast to the future. In a moment, you go to the future. So if you could go near to a black hole, we don't know where is the nearest black hole. We know there's a huge black hole in the center of the galaxy, but that's far away. But we know the galaxy is full of stellar black holes. So maybe we're going to see one not too far. And I hope that not me, but I don't know, my next generation, somebody could be able to go there. And then we'll have to rearrange our thinking of time, taking into account this variability.
Up on the balcony, I think. The wave person
hello,
on the balcony?
hello.
Yes, okay.
Yeah.
There you go.
When thinking about gravity and the fabric of space-time, should we now change that to space entropy? Will that make sense?
Space entropy?
Yeah.
Well, yeah, that's one. Yeah, absolutely. That's one of the open problems in theoretical physics. In fact, it's one of the most clearly defined and less traveled, less studied problem in theoretical physics. We tried to write some number of papers on that, but I'm not sure we're going very far. Everything has entropy, okay? A gas has entropy. The electromagnetic light has entropy. The heat inside a hot cavity has entropy. The sun has entropy. I have entropy. The gravitational field has entropy. So space has entropy. And so we are able to compute the entropy, we can be able to precisely compute the entropy of all these things except for space. We don't know how to do the thermodynamics of space-time itself. It's one of the open problems in physics. Not only we don't know how to do the quantum mechanics of the gravitational field, but we don't even know a simpler problem, which is just simply the statistical mechanics, the thermodynamics of space-time, which is the gravitational field. So the entropy of space has to be well defined, but we don't have a good definition of it.
Here to the left, somewhere around. Yeah.
So in quantum mechanics, there's this idea of measurement which has sort of an effect on what a particle is, and sort of measuring the particle is what defines sort of whether its position or its velocity. And if it's not being measured, it's sort of uncertain where it could be, for example. So could time not just be a feature of the world being constantly sort of measured, and that if there aren't particles interacting and being measured constantly, that time is actually not defined, and sort of that time would come from this measurement?
Okay, so good. A few steps. Let me break the question in pieces. Definitely, at least I'm strongly convinced that time being a variable like any other, because it's always clock time, the time we deal with, is the observable time. It's a variable like any other, so it's a quantum mechanical variable, so it works like any other. So it only becomes determined when we measure it. That's, I'm convinced. Which is another way to say that gravitational field, it becomes a quantum object like anything else. It's going to be quantized, so it behaves quantum mechanically. Having said so, let me step back to your question. What you said is exactly what is written in textbook about quantum mechanics, which I think, on which, as you know, there is a huge debate, and strictly speaking, obviously, is meaningless, right? As what the universe know whether I'm measuring something or not, right? If I'm not on Andromeda, it doesn't mean that nothing happens on Andromeda because none of us is measuring there. It's just obviously silly. So I think, and this is where opinions diverge, how to make sense of that, and that's called the interpretation of quantum mechanics problem, on which there are open debates. This summer I'm going to Oxford to have a big public debate at 2 with an Oxford philosopher who has one interpretation of quantum mechanics. I have another one, so we're going to debate publicly. This is a British Association of Philosophy of Science sponsoring this debate in its annual conference. So that's to say, it's a discussed thing. The way you think about this is that the word measurement is a wrong word. The right word is interaction. So when a system interacts with another system, not is being measured by a physicist with a white thing, you know, male, white, with a PhD. I mean, it doesn't make any sense. Who is measurer? Like is a dog a measurer? But a measurement happens when two systems interact. So the way we have to think about the world quantum mechanically, in my opinion, is that we can think of the world split arbitrarily in subsystems, and the way each subsystem behaves is by being measured by others. And so things become well-defined in the sense you were saying, including time, at interactions. That's why when I was saying the microscopic picture is this flickering probabilistic thing that are actualized in each interaction.
Fewer questions from this side of the room here. If you've got questions, anyone on the balcony up there, you've been very quiet, so I know you've been listening. Or down here, yes, brilliant.
Thank you very much for a wonderful talk. I just wondered, because you mentioned the Buddhist angle, and I know that spirituality is always a bit strange when you link it to science. But in Buddhism, there is the belief that the universe has no beginning at all. And I was just wondering, given that time is a variable of the universe that we live in, or the bubble that we live in, does it even make sense, the obsession that we have to find the beginning of everything? Is there an order, like you said, an absolute order which existed at a certain point and then it just changed? I mean, perhaps this obsession that we have comes from the fact that we are dominated by time.
Yes, yes, certainly this is a possibility that this obsession with the beginning, it's a wrong question, right? This is an old idea. Stephen Hawking have explored this idea in detail, right? You say, what's before the Big Bang? It's like asking what's north of the North Pole. It's just not the right question. There's nothing north of the North Pole. You can just continue through. And the Big Bang might be something like that. When we think of the universe as a whole, we have this notion of cosmological time, which is not a wrong notion. It's just one of these averaged approximations in which we disregard all this fine structure of the universe. We give this very, very wide view of the universe at large, and in that sense we can choose one surface of now pretty arbitrarily and ask what happened. And it might be, as Hawking supposed for a while, that this slicing goes wrong at some point, and there's no meaning before. We're not sure. And in fact, today we don't know what happened at the Big Bang, right? But there's a lot of work trying to apply quantum gravity to the Big Bang. And the indications that I see, and there's a quite big part of the community that think that, is that no, what's actually happening there is different. This approximation can be continued, and we can keep giving the story of what happened before the Big Bang. And roughly the idea is that you can think of a large universe compressing and contracting, getting to a sort of a minimal size and then bouncing up. And that's what we call the Big Bang, this bouncing of the going through a quantum phase and then reopening up. And when we look back in time, we're seeing this bounce. So a lot of people studying whether we can give a description of this bounce and see traces of that. And that's another thing. I hope before dying of knowing whether we can properly think about before the Big Bang or not. I don't know.
I think we've probably got time for one more question. Somewhere up on the balcony. Yep, up there. Give us a wave so you can see how you are. Yes, off you go.
So I understand that fields have quanta, like the electromagnetic field and the photon, but I've wondered, what is the quanta of the field of space-time, or is there just no such thing?
Oh yes, there is such thing. And in fact, loop quantum gravity, the theory in which I work, is a mathematical description of the quanta of space, of quanta of space-time. You can think it's the elementary chunk of space in some sense. These are the Planck size elementary bits out of which space is in their quanta. They're linked to one another, and there's all this link, and you follow this link and you make a loop. That's the name loop quantum gravity comes from. Now the key point, the crucial point, is that you have to think of these bits, this quanta of gravity, not as things immersed in space. So there isn't a space and this quanta here and there. They are space themselves. They made up space themselves. So we call space, it's a collection of these connected to one another. And what we call distance is sort of numbering of how many of these. What we call time is how they transform into one another continuously, is the number of steps of this transformation. So these are quanta, but they're not like particles. No? The particles of particle physics are the quanta of the field. The photons are the quanta of the electromagnetic field. But the photons are little chunks of energy that travel in space, while the quanta of gravity are a little chunk of gravity or something, which made up themselves space, so they don't live in space. It's like, this is a constant, my analogy, if you look at my t-shirt, it's not that my t-shirt has threads in it. If you take away the threads, it's not the t-shirt still there, there's nothing. So the t-shirt is just weaved by the threads. So space itself is weaved by this interconnected quanta of gravity. This is the core of loop quantum gravity.
Right, well, we have run out of time, whichever version of time you're using today in your head. Might have changed a bit in the past hour and a half. So Carlo will be signing books outside, and please let's give a huge thank you for this fabulous evening. Thank you, Carlo Rovelli.